We'll get started in a minute or two. All right, so what I want to do today is talk about something that is sort of on the assignments. Periodic optical systems are on your next computer assignment. I'm going to talk about them in a bigger context. So this is all part of a big field called photonic crystals or photonic band gap materials. It's something that I spent a whole lot of time on in grad school, although I haven't worked on it as much lately. It's a very big field, it's very visual, so I pieced together a bunch of different slide presentations that various people have made available with far better figures than I could put together in a couple days. And then I put together some theory at the end. So start off reminding you of a few things. These are slides you've seen before. If we have two waves, and we interfere them at an angle, then we can produce a periodic light pattern on a substrate. And this pattern is periodic. Okay, almost all light waves are periodic, but this pattern has a time averaged intensity profile that's periodic. Normally, a light wave is periodic, but it's oscillating. So as it's traveling, first the light at this point will be at a maximum, then the field will be 0, then a minimum, then back to 0. So normally the time average intensity at each point is the same, but you can produce these interference patterns. And when you have these interference patterns, then you can write a periodic pattern into a photoresist. And I showed you pictures of how I did that in grad school, and we actually wrote and sculpted three-dimensional periodic patterns. Now, we already talked a little bit about periodic systems, and you're in the process of playing with a periodic 1D system. And in a periodic 1D system, you wind up getting bands of nearly perfect reflection and bands of at least partial transmission. And this is why they call it a band gap material, because there are gaps. You know, here you've got at least partial transmission, meaning the reflection is not 1. The reflection may be a complicated oscillating function, but it's not 1. Then you've got a band of essentially perfect reflection, which means forbidden transmission. Then a band of, again, transmission, a band of nearly perfect reflection, a band of transmission, a band of nearly perfect reflection. And so these bands of nearly perfect reflection are called band gaps. They're gaps between frequency ranges or wavelength ranges where propagation is allowed. Here propagation is allowed, here propagation is allowed, here propagation is allowed, but in between there are band gaps where propagation is not allowed. And periodic gratings also do something similar. They take light and they shape it so that light can only travel at certain specified angles. Now, on one level, that looks completely different from this. But on the other level, if we go really deep, not even into relativity, just into the wave equation treats the three spatial coordinates and time on essentially the same footing. And more importantly, the wave equation relates the periodicity in time, or the frequency in time, to the periodicity in space, or the spatial frequency. So essentially what's happening here is that only certain spatial frequencies of propagation are allowed. The light comes through here, and it can go at this angle, or at this angle, or at this angle. Sorry, it can go either straight to the right, or up at this angle, or down at this angle. So only certain spatial frequencies are allowed to propagate once it passes through there. It takes all this light and it forces it into certain spatial frequencies where propagation is allowed. Likewise here, only certain temporal frequencies and hence spatial frequencies were allowed. Similar things happen if you have a 2D periodic surface. So here what we've got is at the top essentially opal gemstone. Right? An opal gemstone produces these interference colors. We've talked a little bit about them before. It's just many layers of silicon dioxide particles and produces these interference colors. Here's an electron microscope image of it. And we're looking at one particular facet of it. And then here's what happens if someone shines a green laser on it. You get a pattern that looks not so different conceptually from this, where light was only allowed in certain directions. Here, of course, you could say, well, come on, there's green light everywhere. Yeah, there's green light everywhere, but the green light is particularly dramatic here, 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 at this square array of points. And there are reasons why these streaks show up. But in general, you get your strongest propagation into these little dots. And out here, in here, you get a lot of stuff mixed together. But then if you look further out, you see a second dot, and you see much less stray light in between. There are reasons why. You've got a bunch of stray light in between the central dot and the first dot, but not nearly as much between the first dot and the second dot. And it basically comes down to the type of disorder that shows up in the system. It comes down to the fact that the system isn't perfect on the large scale. We know it's not perfect on the large scale because you see some defects here, some defects here. Defects just meaning deviations from a perfectly square grid. So you see the occasional defect, but the defects are mostly far apart. And details that are far apart in the object always show up, have effects that are close together in the diffraction pattern. On the small scale, you look at it and you see that, well, for the most part, it's pretty periodic. You have to go many particle diameters before you see another imperfection. So small scale features of the object show up in the large scale features of the diffraction pattern. So again and again, we see that periodic systems force light into certain frequencies. They only permit transmission of certain frequencies. They only allow scattering at certain frequencies. And this is the idea of a photonic band gap material. And this is not so different from a crystal that electrons propagate in, all right? I mean, instead of having, if you think about electrons, they obey a wave equation you learned in quantum mechanics. And in that wave equation, you've got a potential energy term. Well, in the wave equation, we've got a dielectric constant that fulfills many, not quite all, but many of the same roles as the potential energy in quantum mechanics. And as a result of that, we get these periodic propagating states. So let's switch. I'm going to go through a few different courses of slides that other people put together. You could teach a whole class on photonic crystals, a whole semester. I'm just doing a day. The basic idea is that you can have a system whose dielectric constant is periodic in one direction, two directions, or three directions. This actually shows up in light. There are many animals that on the microscopic scale exhibit these periodic patterns. You look at some of their features And they chose the sea mouse. A better example, I think, is a lot of beetles. I mean, there are beetles crawling, there are insects around here in this area that when you look at them, you see different colors from different angles. And this was known on some level for a while, and it was particularly these things. People have been making these things forever and studying their optical properties. And there was a vague awareness that there are analogies between the optical properties of this periodic system and the wave properties of electrons in metals or semiconductors. And then in 1987, around the same time, Eli Yablonovich and Sajeev John, working from two completely different perspectives, both within like a month of each other, published articles on the same idea. Eli Yablonovich was thinking about how to control the emission of light. He had this idea that, hey, we routinely build cavities that light bounces back and forth inside of. And people make microwave cavities in 3 dimensions. They're boxes. You probably have one in your kitchen. What if I had a periodic system that light is bouncing back and forth in? Then I could control the wave states of the light the way that metals and semiconductors automatically require electrons to only travel with certain wavelengths and frequencies. Meanwhile, Sajeev John, more of a theoretical physicist, was thinking about localization. It had been known that a disordered material does not conduct electrons. If you have enough disorder in there, you can actually get it's an insulator, all right? And insulators can come about via a number of mechanisms. Disorder is one of them. And Sajeev John was thinking about, what if we took a periodic system and then started perturbing it? Could we go through that same metal insulator transition for photons that we see for electrons in disordered materials? And so this has led to all sorts of different work on omnidirectional reflectors. Some people realized that they could make better fiber optic cables for certain applications if they put a periodic system around a hollow core. Can anybody think of why you would want a hollow core fiber? Well, if we have a really, really strong pulse of light, which sometimes you need, there's always the danger that that strong pulse could damage the fiber, or if not damage the fiber, very strong pulses of light actually change the optical properties of whatever they're traveling through. And sometimes people take advantage of that. Sometimes people use that fact so that if they know how the optical properties are going to change and they come up with a system where when you change the optical properties in this way, you get that kind of response, and it's the response that you want. Sometimes that's not how it works. So if you can make a hollow core fiber, then you could have most of the light traveling in air. There'd still be a little bit of evanescent wave in here, that's inevitable, but the evanescent wave would be weak, this wave would be strong, and furthermore, this part of it is going to be made out of a different material than this part, so you could say, all right, in here we've got a field that's intermediate strength, there might be some sort of nonlinear effect, we'll take that into account. Here we've got a system where the periodicity only allows certain frequencies to propagate, and this light is at a forbidden frequency, so it can't go into the periodic system. So you carve out a channel in there, and the light is confined there, and you can get it to do a sharp 90-degree bend, something that light can't do in a fiber optic cable. Fiber optic cables have to bend very gradually, whereas here you get a sharp bend. People can pattern materials in 3 dimensions. There's lots of ways. I already showed you some pictures of little colloidal particles that spontaneously self-assemble into these periodic arrays. It turns out that by geometry, that's just the best configuration for them to go to. It's the configuration of maximum density. There's a reason why at the grocery store, oranges and other spherical fruits are often stacked in these hexagonal lattices because it's the densest possible packing of a bunch of spheres. So you could take a bunch of spheres and you could pack them. And then you could put stuff in between the spheres. And the stuff that you put in between the spheres will then form a network. And then there are ways to etch out or burn out the spheres that were initially forming the network. And what you're left with is the stuff joining, the stuff that was put in between them. I actually spent a bunch of time in grad school trying to do that. You can do it, but doing it over large areas to make something useful is incredibly difficult. People have found that these Lincoln log structures often have nice optical properties. So a lot of work has gone into fabricating these through basically the same techniques that people use to make integrated circuits. The physics is easier to understand in 2D systems, and the fabrication is also easier to do. So oftentimes people will focus on 2D systems. They can make them square, they can make them hexagonal. And then these systems have something called a band structure. There's a relationship between frequency and wave vector. But this wave vector is a little bit different from the K that we've been using. I'll derive the details of it later. But this wave vector is not something that's telling you the phase everywhere in space. It's telling you the phase difference between here and here, one lattice period over, or here and here, one lattice period over in a different direction. All right? So these wave vectors have a different meaning. And it's actually something, again, that shows up in quantum mechanics, where if you've already taken, one way or another, you've probably seen plane waves in quantum mechanics. And you've got these plane wave solutions to the Schrodinger equation. They're e to the I kx, or maybe you write e to the I p times x over h bar, e to the I momentum times x over h bar. They're very much like plane waves of light. They have essentially the same mathematical properties. The physical interpretations are rather different. But then you put them in these periodic systems, and all of a sudden the phase relationships become a lot more complicated. And so you get these weird band structures, and you get these forbidden frequency ranges. Working in this field, you'll see over and over again diagrams like this. And it's usually the band gap that people want. And the trick is to get an omnidirectional band gap. A band gap so that no matter what direction you're traveling in, a certain frequency is forbidden. Now, that's actually somewhat hard to achieve in 3D. In 1D, it's guaranteed. In 2D, it's very, very common. In 3D, it's actually very hard to achieve. And basically, the way to think about it is that the geometry is not the same in every direction. This direction is different from this direction, all right? And particularly the spacing along this direction is substantially shorter than the spacing along this direction. And so whatever is happening here is going to, the interesting physics here will involve short wavelengths. The interesting physics here will involve long wavelengths. And then you have to get that reflection peak spread out along a range of short wavelengths. You need to get the reflection peak spread out here along a fairly wide range of short wavelengths, such a wide range that some of those wavelengths can no longer really be called short. And here you have to get all of your interesting physics to happen over a range of long wavelengths, such a wide range that it extends into some short wavelengths. And if the interference effects here, the gap here overlaps with the gap here, then you have a complete gap. You have two overlapping gaps, and the parts that overlap, well, those are frequency ranges where nothing can propagate in any direction. And that's a big thing. And people very quickly figured out on paper what kinds of systems will give complete band gaps. But it's one thing to write down on paper, okay, you just make something with this refractive index and that refractive index combined in these shapes, and there you go. And it's quite another thing to actually make a pair of materials with this index and that index, or usually just one material surrounded by air. It's the ratio of the indices that matter. To pattern something with the desired index, it usually has to be a high index to get really interesting stuff happening, because if you have a very small index contrast, then you get a very narrow gap, which means that the gap along this direction will be narrow. The frequency gap for stuff traveling in that direction will be narrow. These two narrow gaps don't overlap each other. Whereas if you have high refractive index, well, you've got a gap you've got a range of forbidden frequencies for stuff going in one direction, a range of forbidden frequencies for stuff going in the other direction. If you look at my fingers, you see that there's some overlap of those gaps. And then that overlap, you get the complete band gap. So you have to pattern a high index material in exactly the way that people want. And patterning these things in 3D is often really hard. What they basically do is, on the theory side, they start with Maxwell's equations. It turns out to be more convenient to work with H. Remember that B is mu times H. So they work with H, and then they go from having 4 equations to having just one equation. They eliminate E, and they get this equation, which doesn't look exactly like the wave equation that you've seen before. But if you use some vector calculus identities, then this equation is the same. And we take advantage of the fact that 1 over epsilon is piecewise constant. You know, if you've got a mixture of silicon and air, inside silicon, it's 3.1, 3.6. Well, n is 3 point something, so n squared is like 10, so 1 over epsilon is 1/10. Outside of it, in air, 1 over epsilon is 1. And so this is a constant everywhere except at the boundaries. And at the boundaries, they have mathematical techniques for dealing with it. So you get a wave equation, and then you look for the eigenvalues of this operator in the wave equation. In quantum mechanics, those eigenvalues are the energy. In electromagnetism, those eigenvalues are the squared frequencies. And I'm going to skip some of that, and I think I will skip to here. So let's take the really simple system. Air, vacuum, right? Omega is just equal to K. Nothing particularly profound to say. The bands are linear. And notice in systems like that, near zero frequency, the band starts off linear and then starts to curve. Likewise over here, where you're going from a high frequency to 0, because basically what you're doing is you're going from here to here, back. Going along this axis means you're looking at K vectors that first you've got a range of K vectors, all of them in the horizontal direction. Then we start adding vertical components. Then we go back, all right? Near zero frequency, it's linear, just like vacuum. But then as we start adding in the periodicity, when K is roughly pi over the spacing, all the physics becomes complicated. And so things start to change. The dispersion relation starts to change. And that is how you get these gaps. I think I'm going to skip that and go to another talk that's full of interesting, full of pictures. Any questions so far? That first set of notes was from a site called NanoHub for nanotechnology education. There's actually no author listed there. The second set of slides is from a guy in the Opals group at MIT, which has been a real leader in the field of photonic crystals since the late 80s, early 90s. And by the way, Opals wrote a really great introductory level book on photonic crystals. It's what I used when I was first studying this subject in grad school. I was just a first-year grad student, so I had basically the same coursework as you guys. All right, again, same stuff. More examples from nature, butterfly wings and feathers showing different colors at different angles. And here is an electron microscope image of something like that. And biology self-assembles these structures spontaneously. And then we can engineer defects into these periodic systems and trap light. There are close analogies with waves and electrons. If you study, with electrons and solids. If you study electrons in solids, you get band diagrams like this showing how the energy is related to the wave vector. And that's actually kind of, it solves a mystery that if you just think about it for a minute, you realize, oh yeah, that is a problem. Think about electrons in a crystal. You've got these electrons traveling, you've got these positive nuclei everywhere. And they're constantly being diverted by the nuclei. You know, an electron is traveling, encounters something attractive, gets deflected at an angle, then it comes on to the next one, encounters it, gets deflected at another angle, gets deflected at another angle. Yet somehow electrical conduction happens. And it's because in periodic systems, you get these periodic solutions to the wave equation. That even though you've got all these obstacles for the wave to bump into, because they're all evenly spaced, somehow the waves are able to take on these shapes that just naturally account for that and travel all the way through. So light can do the same thing, and that is why you see these analogies. That is why these diagrams of energy versus wave vector or photon frequency versus wave vector. And remember, the photon energy is equal to frequency times Planck's constant, and electron frequency is energy over Planck's constant. So these things are even more analogous than they look. Again, they simplify the Maxwell's equations. They get an eigenvalue problem. They deliberately set it up so that the operator they're dealing with is Hermitian. Those of you who have already taken the upper division quantum mechanics know what I'm talking about. Those of you who haven't, don't worry, it's not on our assignments, but we will get to something that is on our assignment. They write the solutions as a plane wave multiplied by a periodic function. And we'll go into that again later, but the K out here is the K that shows up in all of these diagrams on the horizontal axis. Now, the thing is, I've got a periodic function. And of course, I could expand that periodic function in terms of sines and cosines, which means I could expand it in terms of complex exponentials. So I've got a complex exponential multiplied by a whole bunch of other complex exponentials. The difference is that these complex exponentials, they have to form a periodic function. You can say, well, fine, this one's periodic too. Yeah, but this one has periodicity equal to the periodicity of the lattice. So this one repeats going from here to here to here and so forth. And likewise from here to here to here and so forth. And it's periodic along this direction too. So this one is a very constrained function. It's got a whole bunch of complex exponentials with different k values, but all those k values are tightly constrained. This one isn't. This one k can be anything. All right? So what I've got is, I've got this periodic function here, and again here, and again here, multiplied by this phase factor. So what I've got is, I've got the same intensity profile here, and here, and here, and here, and here, and here, and so forth. I got the same intensity profile on each of these repeat units of the system, just with a different phase. So, you know, they might not, the waves might not be oscillating together like this. They could be oscillating like this. They could be out of phase with each other. And that's what this K is telling you. It's telling you the phase relationship between what's happening here and what's happening here. It's no longer the K of a simple plane wave, which is just 2 pi over the wavelength, because this whole function is much more complicated. This is periodic, this is periodic, these periods are different. This K is just the phase relationship between here and here. Any questions? If you take a class on solid state physics, you will learn about this again. Except that instead of talking about solutions to Maxwell's equations, you'll be talking about solutions to the Schrodinger equation. But anytime you have a wave equation in a periodic system, we can do this for electrons, we can do this for photons. People have done it for sound, they're called photonic crystals. Sometimes people talk about using ultrasound to make a photonic crystal vibrate. So you got a photonic crystal, send ultrasound through it, it vibrates, which means that you change the lattice spacing. So now we have a way to use sound to change the optical properties of the system and change some of these solutions. Where else have I seen it? I've seen a little bit of work on water waves, but mostly light, sound, and electrons. I'm sure if I thought about it long enough and did a little bit of searching in Google Scholar, I could find periodic solutions to other wave equations. All right, so when we work on this, we wind up getting different bands. And here we see that this band and this band always partially overlap. So there's no band gap. Here, the very top of this band is a little bit below the very bottom of this band, so we get a band gap. The periodic systems are particularly easy, but I'm going to go through those with pencil and paper a little bit later. I think what I really want to show, besides just noting that periodic systems always have a gap, is I want to skip ahead to all of the applications. Except I should note that the diamond lattice is a particularly promising one for band gaps. The diamond lattice has really good band gaps. And that's actually related to something that I'm sure someone understands it. I don't, I've never studied it. Amorphous silicon turns out to be a useful material. Amorphous silicon, meaning silicon where the atoms are disordered, turns out to be a useful semiconductor, just like crystalline silicon. And the existence of a band gap is related to the existence of forbidden frequencies or forbidden energies where it would be an insulator for electrons, and the existence of propagating states, the things in between the band gaps, or the things that the gaps are gaps between, those are conducting states. And semiconductors have both conducting and insulating states. And amorphous silicon, which locally forms these 4 bonds, just like the carbon atoms in diamond, amorphous silicon is a useful semiconductor, and diamond lattices are very useful photonic band gap materials. So initially, all of these things were studied in computer simulations because doing the calculations is way easier than making the things. But initially, they tried packings of spheres, and they found that you need to have a pretty high refractive index contrast. Diamond is nice because if it's diamond, you can get a lower refractive index contrast. The problem is that assembling spheres into a diamond structure is actually hard. People do layer by layer lithography. Basically, what they do is a cyclical process. You deposit some photoresist, you etch the photoresist, then you repeat. You can make rods and holes simultaneously, so you can extend holes deep into a substrate to produce periodic patterns like this. There's a lot of interesting physics done in systems like this. I am not a semiconductor, a clean room fabrication guy, so I'm going to get the details wrong. People have done these things with electron beam lithography, which is the same stuff used to make integrated circuits these days. People have done log piles. Those are really popular structures. They have very nice band gaps. The problem is making very large log piles is time-consuming and expensive. Two-photon lithography is something we'll get to next week or the week after. You hit something with 2 photons and it absorbs. And the beauty of that is that unless you're right near the focal point, the odds of getting 2 photons to arrive at the same time are very, very low. So you can etch patterns with light. You do more than just make periodic systems like that. People do art like that, usually as, it would be hard to charge a sculpture like this to your grant if that was your end goal, but as a proof of concept for your resolution and scalability. There was something more than a decade ago where people made the world's tiniest violin, etching it out of, I can't remember whether they did it via polymerization with nonlinear optics, 2-photon absorption, whether they did it with silicon processing. But you know, usually in a way, when people are showing off their new technique for getting finer details, they'll make something clever like this. At some point, people decide to make the world's tiniest violin. Holographic lithography, what I showed you earlier, what I worked on for a little while in grad school. You use these interference patterns, and wherever the light is bright in the interference pattern, photochemistry happens, making the system more soluble or less soluble, depending on how you want to do it. People will deposit colloidal particles. You get things that look like that. I spent a lot of time playing with that in grad school. Then you put stuff in between the particles, remove the particles. It's called an inverse opal. And you can get a complete band gap, but the trick again is that you need to have a very high index contrast. So we spend a lot of time putting stuff in between. The problem is that the stuff we were putting in between didn't quite have a high enough refractive index. We wanted to use titanium dioxide, but it turns out that there are at least 2 different kinds of titanium dioxide. There's 2 crystalline structures that you can get at room temperature, and then there's also amorphous titanium dioxide. And the crystalline form that has the higher refractive index is sadly harder to make. And so we were never able to get good rutile, which is the name for the higher index titanium dioxide structure. We were never able to get good rutile in here. People who are experts on silicon processing were able to put stuff in there, but we were not experts on silicon processing, so we were not able to do that. There's a lot of art to getting these colloidal particles to assemble in just the right way. But it turns out that if you just simply take a glass slide and put it in a solution with silicon dioxide spheres and ethanol, not water, but ethanol, turns out to be important, and then let it evaporate, you spontaneously get something very nice like that. You can get something with a very controllable thickness like that, very good order down to the substrate. I spent a lot of time working with the electron microscope taking pictures of these. At some point, people even figured out how to put defects into inverse opals, and then they could write the initials of their university in there and take an image of it. That's a very popular thing to do when someone comes up with a new nanolithography technique, is write their name or write the initials of their university. Personally, I think if I were going to invent a new lithography technique, I would probably use it to write a D&D character sheet into a material, but you know, to each their own. People can do these things with polymers. There are special types of polymers that will spontaneously assemble into spheres or cylinders, or complicated cylinder structures or multi-layers. And so there's a whole bunch of chemistry and material science to those polymers, but those will also form photonic crystals. These tend to form with much smaller periodicity, 50, maybe 100 nanometers. So you're looking at an ultraviolet band gap instead of a visible band gap, but still, it's absolutely fascinating physics, the way that these things self-assemble. Then sometimes they stretch it, because if you stretch it, you change the spacing. And so you can shift the band gap from the UV to the visible. There's something called glancing angle deposition, which I know far less about, but it makes really cool structures. You put these posts on there, and then somehow when you deposit silicon at a glancing angle, it forms like that. Then you rotate, and you produce these weird spiral structures. I mean, I gotta be honest with you. To me, this field, one of the reasons why I studied this field in grad school before moving on, was it makes really cool pictures between things like this, you know, the structures when you simulate them, and the laser diffraction patterns, and the things like this. You get to spend a whole lot of time staring at really pretty pictures for 7 years of grad school. If you've got to spend 7 years in grad school, well, at least look at some cool visuals. They use these things to make something called metamaterials, which I'm not going to spend too much time on, except to say that the refractive index becomes negative and the physics becomes weird, and you can get perfect focusing at short ranges. Let's see, what do I want to say about defects? I guess what I want to do is I want to look for the fun pictures from this talk. So you make cavity modes, all right? You come up with a system that is periodic, and then you put a gap in there. You put a void in there, I should say, because the word gap means a gap between frequencies. And any light whose frequency corresponds to the band gap in here, well, it can't propagate in here, so it's confined. Sometimes you don't put vacuum in there, sometimes you just put a slightly different kind of system in there. So the refractive index here is on average different from the refractive index here, even though the periodicity is the same. You can put just a single cavity there and get a single mode, which means that you get one frequency state in this band gap. So there's only one mode that light can emit into. So you can trap light for a very long time in there. And you can have an atom interacting with that cavity mode. And you can do fascinating quantum mechanical experiments watching an atom oscillate between ground and excited state. People can play with the geometry here. And when they play with the geometry of this defect, either making it small or large, they can either get a monopole state, which means that the light is kind of symmetric, or a dipole state where the light will be antisymmetric and have a preferential orientation. For photonic crystal fibers, you don't need a complete band gap because we want propagation along this direction. So sometimes incomplete band gaps are useful. What else do I want to say? More pretty pictures. You can get 90-degree splitters for light. So if you want to make photonic integrated circuits, this is your stuff. Lossless bends, like I've shown before. Tunneling experiments. So you've got the light confined here. You've got the light confined here. You've got a periodic system in between. And this periodic system is more than 5 layers in reality. So it's still going to block the light. But you put a defect in there. So suddenly at that defect, there's an allowed state. And the light can come in, the evanescent light can couple to that, whatever evanescent light gets in, goes into that defect state that's bouncing back and forth in here. It bounces back and forth a long time, so a lot of light builds up. Even though only a little bit is getting in any 1 second, a lot builds up. You have a large amount of light stored here, some fraction of it gets out, and so you can get a lot of light coming out here. And this is mathematically equivalent to quantum mechanical tunneling. Anytime you can confine light, you can do a lot with nonlinear optics. I don't know how much more I want to say about that, borrowing from this other guy's talk. Do I want to do anything else with his slides? No, I don't think I do. Except to say that fabricating fibers like this is important and fun and leads to pretty pictures and is also employable. Any questions so far? So let's go to the physics of multi-layers. Like I said before, the 1D photonic crystal, its math is easier. And like I said before, we get a periodic system. We get a periodic function, that the field is a periodic function multiplied by this phase factor. So we got a profile that's the same here in this pair of layers, and in this pair of layers, and in this pair of layers. But they're not in phase with each other. There's a phase shift going from here to there to there. And omega of k looks like this. Now you're thinking, wait, they had it folded like this. Well, it's like this. We've got something that looks like this, all right? We've got that at certain frequencies, at certain k vectors, there's a jump in frequency. Basically because at certain k vectors, propagation isn't allowed. If I'm at just the right k vector, then we've got perfect constructive interference of reflected waves, all right? I've got just the right k vector and just the right frequency. We get perfect constructive interference of reflected waves. We've talked about that before. And when I get this strong constructive interference of reflected waves, that means light is forbidden. So at certain k vectors, there are forbidden frequencies. So we jump in frequency. We go up to the next frequency. Then we get to 2 pi over a, and again, if I were to draw the next band, there would be a jump in frequencies. Because basically, if 2 pi over lambda is pi over a, then lambda is going to be half of the lattice period, okay? Lambda is going to be twice the lattice period, so that it goes through half a cycle in each period. Because remember how I said that we have quarter wave layers, quarter wavelength, quarter wavelength? That means we're going to have to go 2 lattice periods to go through a full cycle. So the wavelength is going to be 2 times the lattice period, right? Whenever the wavelength is 2 times the lattice period, or the lattice period, or whenever the wavelength is 2 times the lattice period, or 4 times, or 6 times, we get this strong constructive interference. So you've got forbidden propagation. All right. Now, that's why we get forbidden propagation here, because we've got lambda over 4, lambda over 4, so lambda over 2, so this is lambda. All right, now we have to be very careful about this k, which I'm writing and like with straight lines versus this script or cursive k. Within this layer, we've got something that is for a while uniform. We've just got a sum of two plane waves, e to the I n1 k naught x, e to the minus I n1 k naught x, in here and in here. And in here we've got e to the I n2 k naught x and e to the minus I n2 k naught x. And they've got amplitudes a1 plus, a1 minus, a2 plus, a2 minus. So locally, there's always a wave vector, all right? Locally, there's a value of k as we've always thought about. I just say right here, what's the value of k? Well, it's either n1 k naught or minus n1 k naught. But this combination of n plus and minus n1 k naught waves in here and plus and minus n2 k naught waves in here, this is periodic, because that same combination shows up again in here, and it's multiplied by e to the I big K x going from here to here. And k is a function of omega, so we can invert to get omega of k. So we often plot omega of k instead of k of omega. Now I'm saying that we also tend to fold these diagrams. So instead of this, we imagine taking this part of the diagram and flipping it around so it goes to there, and taking this part and flipping it around so it goes to there. Here's why we do that. E to the ik is a phase shift from one cell to the next. And let's say that k is bigger than 2 pi over a. Let's say that k is 2 pi over a plus delta k. Then e to the ik is e to the I times 2 pi a over a, e to the I a delta k. 2 pi a over a is just 2 pi, and e to the 2 pi I is 1. So if I add 2 pi over a to my wave vector, I haven't changed anything, all right? Adding 2 pi over a to the wave vector hasn't really changed anything. It still gives you the exact same physics, all right? And if we're still getting the exact same physics, then what that means is that this wave vector here is equivalent to something over there. So I don't need wave vectors going from minus infinity to plus infinity. I just need a range from 0 to 2 pi over a, or any other range that has the same width. And so by convention, people usually say instead of 0 to 2 pi over a, they say from minus pi over a to plus pi over a. That is a range 2 pi over a, and it's symmetric. We can talk about the effects of direction. And then if we just narrow our range of k values and we solve the equations, we get multiple frequencies that are compatible with each k value. And that's what it means to have these bands. Now, it also means that there are multiple omega values that give you the same value of k. So there are multiple omega values that give you the same phase shift going from this pair of layers to this pair of layers. Any questions? All right, now let's talk a little more about the gap. I already said that if we've got the gap, well, we've got this perfect construct of interference between this wave and this wave and this wave and so forth. Each time it's going through, it's getting attenuated by a transmission coefficient. After n layers, we've got t to the n fraction remaining. And t is less than 1. So we've got something exponentially decaying, which means we could write our field as some exponential decay factor, e to the minus gamma x, still multiplied by some periodic function of x. And this e to the minus gamma x must be equal to e to the I times an imaginary k times x. So if we're in the band gap, k equals I gamma. Right? So if we solve our equations, and we're going to show our equations in a moment, but whatever equations we get, if we're in that band gap, then suddenly k goes from being a real number to an imaginary number. And that's how we know that we're in a band gap. K is imaginary. E to the ikx is e to the minus something times x, exponential decay. Any questions? Well, there's a lot of ways to get the equations that we would solve, but here's the most simple way, at least in 1D. And actually, you can say similar things, and there are tricks for doing it in 3D. We start off with this form. Then we note that, well, we could also have solved for this with transfer matrices. Whatever the field is here, depending on the direction of propagation, it's just e to the plus or minus ika times the field over here. That's one way of relating these two fields. But another way of relating these two fields is via transfer matrices, which we talked about last week. And with transfer matrices, we just multiply an interface matrix to go from here to here, a phase matrix to go from here to here, another interface matrix to go from N2 to N1, and then one final phase matrix. So you could say, what about the next interface? Well, we already did something to cross from N1 to N2. So when we wind up here, that's equivalent to being here. So if I multiply 4 matrices, I should get back my original field multiplied by a phase shift. Now, whenever you've got a problem in math where you multiply something by a matrix and get the same thing back multiplied by a constant, that's an eigenvalue problem. You've got an eigenvector, and that eigenvector is just going to, when acted on by the matrix, will return itself multiplied by an eigenvalue. And that eigenvalue should be e to the ika. So we multiply these 4 matrices. We get the eigenvalues. We set the eigenvalues equal to ika. We solve for k. Now, where does k naught show up? K naught shows up in these phase matrices because the phase matrix, your phase shift is going to depend on the refractive index multiplied by k naught, which is omega over c, multiplied by the layer thickness. And so we just have to solve this eigenvalue problem. And whenever we get eigenvalues that are complex exponentials, then we've got propagating waves. Whenever our eigenvalues are real numbers, so that our exponent, so that our k, I wrote imaginary eigenvalues, I should have written imaginary k, we've got a band gap. Any questions? All right, so I did that in Mathematica. I set up those equations. First, you define your interface matrix and your phase matrix. Then we multiply 4 matrices together, we get something messy. If we solve for the eigenvalues, I put in a small refractive index contrast. I could have put in something else, but I put in a small refractive index contrast. I solve for the eigenvalues. I get something messy. All right? Then I look for the and I just realized that I should be taking the log of all of this. You know what? When you try to change your Mathematica file on the fly, things go wrong. Let's just take it as a given that if I plot, here I'm plotting K versus omega, and I haven't had enough chance to play with it, and that's my fault. I should have tested this more. But let's just take it as a given that we are seeing some alternating bands of, we're seeing some alternating behavior in the K versus omega instead of omega versus K diagram. And I apologize for not catching the mistake in the file sooner. But that's the idea of it, that we would set up those matrices, find their eigenvalues, and then extract K from the eigenvalues. Any questions? If you take nothing else away from this, if all you're thinking about is next week's assignment, keep two things in mind. One, this explains why there's exponential decay. You're looking for exponential decay of transmission with increasing thickness. If we're working in the band gap, then every time we go from one layer to the next, we're multiplying by a transmission coefficient. If you've got n layers in a row, you've raised your transmission coefficient to the n power. And if the thing we're raising to the n power is less than 1, we've got exponential decay. The other thing to take away is that you're going to probably find that higher refractive index contrast results in more rapid decay. That's basically because you've got stronger reflection at each layer. And it's also related to the fact that when you go from when you've got very large refractive index contrast, you get wide band gaps. Any questions? Then I want to show you one last thing that I learned about in grad school. Around the time that I started working on photonic crystals, I took a solid state physics class from a guy who wanted us to remind us that some things are neither periodic nor disordered. So I'm just going to show you a few pictures right now. Let's start with, of all things, Wikipedia, because the Wikipedia article actually has some good stuff here. Let's look at the Wikipedia article on quasicrystals. A quasicrystal is something that's definitely repeating. If we look at this, we see repetition, but it's not periodic, because if I go from here to here, I get repetition, and then I don't. You can see the center of a ring here and the center of a ring here, and a similar structure there, but it never quite repeats. There are systems, it's definitely symmetric. It has symmetry to it. It has 2, 4, 6, 8, 10-fold symmetry. Definitely has 10-fold symmetry. Definitely has motifs that show up again and again, but it doesn't quite repeat. And it's called a quasicrystal. Here's the simplest 2D quasicrystal. It's called the Penrose tiling. It has 5-fold symmetry. You'll never find a truly periodic system that has 5-fold symmetry. Yet this thing definitely has a repeat unit that shows up again and again. If you look at this, you can find this repeat unit showing up. And it's made out of some much simpler units, 2 diamonds of different aspect ratios made playing with different colors here. And this is a very common type of quasicrystal. Even in 3-dimensional quasicrystals, often one of their surfaces will look like this. 5-fold symmetry is forbidden for truly periodic structures. It's not forbidden for quasi-periodic structures. And just as we can get 5-fold symmetry, truly periodic structures can have 2-fold, 3-fold, 4-fold, and 6-fold symmetries. You can't go to higher symmetry than that. But these quasicrystals, well, you can have 5-fold, you can have 10-fold, I've heard of 12-fold symmetry. And one thing you should notice here is that this whole system looks almost circular, okay? keep in mind that when we were doing the square system, I said that going this way versus going diagonally, the physics was different, because going horizontally, you've got a small spacing. Going diagonally, you've got a large spacing. And so trying to get the horizontal the frequency gap for horizontal propagation to match up with the frequency gap for diagonal propagation, that's hard. But here, you've got something that spacings are pretty much the same in all directions. So quasicrystals produce interesting photonic band gaps because even though they're not quite symmetric, they're almost symmetric. So you get a lot of the same mathematical properties, and all of the directions are closer to being equivalent. The spacings are more similar in all directions. So it's easier to get band gaps in different directions to overlap. So these were discovered, well, the mathematics of them was discovered in the 60s. The experimental evidence for them came in the 80s. If we look here, we see an electron diffraction pattern with, let's see, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-fold symmetry. You see how these rings are almost circular. You know, this direction here, this length here, and this length here. They're different, but they're not as different as the difference between, say, the edge and the diagonal along 45 degrees if we had a 45, 45, 90 triangle. So, you know, the diagonal of a square. So the difference between this and this is not as big as the difference between the diagonal of a square and the edge of a square. So it's much easier to get band gaps here. And so some people play around with that. Now, the mathematics of quasicrystals is beautiful. It's also complicated. So we don't always focus. You could do a lot of interesting physics, though, with one-dimensional quasicrystals where the geometry is much simpler, and you use something called Fibonacci multilayers based on the Fibonacci sequence. In the Fibonacci sequence, each term in the sequence is just equal to the sum of the two previous terms. Well, here you've got B and A. So the sum of them would be BA. Sorry, B and A and B. So you got BB. Oh, Alex, what are you doing? B and AB. So then BAB. But then the next two would be AB, BA. All right. So it doesn't quite repeat itself. All right. It's based on the Fibonacci sequence. And now, because it's 1D, we just have to multiply a bunch of 2x2 matrices that follow a simple rule that the next set of matrices is the combination of the two previous sets of matrices. And you get these fascinating transmission spectra that they show gaps, and then within the gaps, there are details. It's almost fractal. So you can get very rich transmission spectra, very rich details in the transmission spectra that are much more complicated than the ones you've seen when playing with the periodic films. And they just follow the Fibonacci sequence. Of course, people also do quasicrystals in higher dimensions. But there's a lot of fascinating physics to be done in one dimension. And then the one-dimensional quasicrystal, one of the beauties of the one-dimensional quasicrystal is that it is a projection of a two-dimensional crystal. So let me find that. All right, the one-dimensional Fibonacci sequence. If I drew a line at just the right angle, here we've got a two-dimensional periodic system. It's a two-dimensional periodic system of sticks. All right, if I draw just the right line in this two-dimensional periodic system of sticks, I wind up getting a pattern of crossings. You think of the gaps between these sticks as being the thicknesses of alternating layers. I wind up getting a pattern of crossings that matches the Fibonacci sequence. I don't claim that any of this is obvious right now, but it's a fun problem to play with. And because it's a projection of a two-dimensional system onto a one-dimensional system, it's something that you could do without a ton of additional theoretical training. It's something you could work on with the background that you have. Yet because it's not a periodic system, the physics of it is quite rich. And so I'll just throw this out there. If anybody would like to do a senior project on Fibonacci quasi-crystals, on studying the higher dimension, the two-dimensional problem, which is still computationally feasible, and the one-dimensional problem, and studying some of the mathematical properties of this two-dimensional problem, which is almost like the wave equation that we're used to, but not quite, talk to me. There's a lot of rich physics to be done here in a system that has low enough dimensionality that you don't need either a giant computer or a whole bunch of really sophisticated techniques. The final thing I would say about that is that I know a guy at UCLA who gave a talk here about a year and a half ago, and he made a 2D quasi-crystal out of specially fabricated colloidal particles. And here is his 2D quasi-crystal. Here is a picture of it, and here's a laser diffraction pattern of it. And the laser diffraction pattern of it is also a quasi-crystal, and it has tenfold symmetry to it. The quasi-crystal itself has fivefold symmetry, but because the light behaves similarly in opposite directions, the laser diffraction pattern has tenfold, the Fourier transform has tenfold symmetry, and the laser diffraction pattern has tenfold symmetry. And the laser diffraction pattern is just really, really beautiful to look at. And so another thing you could do if you're interested in studying the physics of quasi-crystals is spend some time studying these diffraction patterns, looking for the property, looking for, say, their fractal properties versus the more mundane properties. It could be a fun problem to play with. Any questions on anything? All right, so that's all for today. The computer assignment on Bragg diffraction gratings on, distributed Bragg reflectors is due next week, and then there will be an assignment posted on polarizing beam splitters. Next week, I'm going to talk about photons and fluorescence, then shot noise and light detection, and then I'm going to talk on Thursday about the Bell inequalities, which are an application of polarizing beam splitters, and also get pretty deep into quantum mechanics. Have a good day.